Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. Today, we are going to talk about a new chapter, which is the probability theory. And today we are going to talk about the probability definitions and set operations. The chances are high that you will face at least a couple of probability problems in most quantitative interviews, because probability theory is actually the foundation of almost every aspect of quantitative finance. As a result, it has become a popular topic in quantitative interviews. So again, we are going to have a chapter overview before we start to talking about specific questions. You can see actually it includes more than 40 questions, which is the largest number for all chapters in the green book. And it covers basic things like the probability definition and set operation, which we are going to talk about today. And there is combinatorial analysis, which is about permutation and combination. And then we have conditional probability and Bayesian theory, and discrete and continuous distribution, and expected value, variance, and covariance, and last but not least, all the statistics. So, and the main items or the main question formats is basically coin, dice, ball, and cards. These four bodies is going to accompany you in all quant interviews, okay? So although good intuition and logic may help you solve many of the probability problems, you still need to having a thorough understanding of some basic probability theory knowledge. Furthermore, probability theory it is extremely valuable in explaining some seemingly counterintuitive results, no matter it is theoretically speaking or in the reality. And so armed with little knowledge about that, it's definitely good for you, no matter during the interview or just in your daily life. Okay, so let's start. Let's first go through some basic knowledge about probability. We're going to have an outcome space, which is the outcome of an experimental or trial. Let's use an example. Let's see if we are rolling a six dice, okay, a six-sided dice. And the outcome is what? The outcome has six possible outcomes, which is 1, 2, 3, 4, 5, 6, right? And this is what? Our sample space, right? And each time we are going to have one outcome omega. And this is large omega where it is all possible outcomes, 1 to 6 integers. And this P omega is going to be the probability of this outcome. And we know for any of y in our example, it is going to be 1 over 6, right? We have 1 over 6 to get a 1 or 2 or 3 or 4 or 5 or 6. And for each event is a set of outcomes or a subset of the sample space. For example, let's say an event is that having 3, 6 in a row. I don't know if you guys have ever played the airplane chess, fishing qi. So at the beginning of the game, you must having a sex to let one of the airplane take off, right? And there are some basic set operations. This is called union, which is the set of outcomes in either event A or event B. Let's use the Venn map. So if this is A, this is B, then this one is a union, okay? And what about the intersection? The intersection is this smaller part, okay? This is the intersection. And if we have a larger map, for example, let's see this place, then this part is what? Let's cover this one. It's going to be AC, right? All places outside of this A circle. And mutually exclusive means that A and B has no intersections, okay? And for random variable, it is a function. Remember, I know all of you knows what is random variable. You know it is y, it can be x. But what I want to emphasize here is that it is actually a function that maps each outcome in the sample space into a set of real numbers. please, it's very important to think any random variable as a function, as a f omega, okay? Because in the future, when we're talking about conditional probabilities, let's say expectation of some kind of conditional x equal to x or y, we are going to say this one can be written as a function of x. It is driven from here, okay? Because it is actually a function, and when you think it as a function, then you can take integration, you can take derivatives, you can do a lot of algebra to that. And that is going to be super beneficial to the solving, to lead you to the solution. Okay? And now let's come to the main principle for solving all the questions in this chapter. I think the best weapon for set questions is symmetry, and think about what's the same and replace. What does it mean? So let's just still use this six-sided dice example, okay? We know the probability of having one, okay, is equal to probability having two, equal to probability having three, having four, having six, equal to 1/6, right? Which means the probability of having one is basically the same as having two when it comes to the probability size, right? So basically, we can think each of them as the same ball, a same red ball, a same blue ball. So they are replaceable with each other, and we can group them together or separate together, 化整为零 or 化零为整. Okay, so let's see how powerful this is. The first question is coin toss game. So two gamblers are playing a coin toss game. The gambler A has n+1 fair coins. The gambler B has n fair coins. So what is the probability that A will have more hands than B if both flip all their coins? Well, it seems a little bit confusing of how to start to solve. What was our first step to solve this problem? Well, the thing is that, remember in the last few chapters, we often use the thing like, let's first give one try, right? We first threw the first coin, but this is not going to be useful in this question. But there is another thing that we could be useful is that take one step forward or backward. What does it mean? Okay, now in our real game, gambler A has n+1 fair coins, while B has only n fair coins. But let's assume okay, only have n fair coin as the same as B. Then what's the probability that A will have more hands than B if both flippers own their coins? So while basically it is going to be probability A larger than B, probability A equal to B, probability A smaller than B. We know the sum of all these three is going to be equal to 1, right? Sum equal to 1. And 1, 2, 3, 1 is going to be equal to 3, right? The probability A larger than B is the same as the probability A has fewer heads than B, right? But by the principle of symmetry. And now this is the case that n has n coins. And in our example, n is going to have one more, right? So let's say if A already have more coins than B, then no matter this n+1 coin is head or tail, A still has more hands than B, right? Probability A n+1 larger than B is going to be 1, right? But if A has less hands than B, then no matter n+1 coin is heads or tail, probability A n+1 larger than B is going to be 0. Right? And now we see what? The only thing matters is that when after each one throws their nth coin, if the number of heads is the same between A and B, and now the n+1 coin that really matter. Okay, and we know that it has 1/2 probability to have a head for the n+1 coin, right? And now can you solve this question? Yes. So basically, the total probability is 0.5 because these two are the same. So let's denote it as P, right? And the probability A equal to B is going to be 1 minus 2P. And the total probability AN plus 1 larger than B is going to be what? 1 multiplied by B, P plus 0 multiplied by 1 minus by P again, right? By P, sorry. Plus 1 over 2 multiplied by 1 over 2P, right? And this is going to be 0.5, okay? And this is our solution. You see, why am I saying that the thing was the same and symmetry and replaceable is very important? We are first finding out PA larger than B and PA smaller than B is symmetry. And hence they are replaceable with each other. And then we can solve this question very fast. Now let's come to our second example. So the second example is a card game, where a casino offers a single card game. There are 52 cards, just to exclude jokes. So one interesting thing is that in Chinese, we have 大小王, right? But it is called red joke and black joke in English. And usually in Texas Hold'em and all other classic cards games from Western world, usually they exclude the jokers, okay? So you can see there are only 52 cards because the 2 jokers are excluded. And each time the cards are thoroughly shuffled, so each card has equal probability of being selected. It's just a one assumption to make the fair question. And you pick up a card from the deck, and the dealer picks another without replacement. Okay. If you have a large number, you win. If the numbers are equal or yours is smaller, the house wins. Okay. I think all other casinos, the house always have better odds of winning. And what's my probability? Okay. Again, so if my number is larger, I win, right? But let's first think about, again, think it from a symmetry way. We have 3 events, right? Events A, events 1. So this is my car is larger than the dealers. Event 2, my car equals the dealers, right? And event 3, my car is smaller than dealers. Ongjun finds that this is quite same structure as our last question. So again, event 1, probability event 1 is going to be the same as probability event 3, right? And the probability of event 2 is going to be 1 minus probability 2 multiplied by probability event 1. And now we only need to solve the probability event 2 to find out the probability of event 1. And it's quite easy. So if I have drawn a card, right, no matter what it is, let's say I have drawn 2, okay? Let's say I have picked a 2. And what's the probability that it is going to be the same card? It is 3 over 51, right? Because after I have drawn a card, then there are only 51 cards left, and among them there are only 2 left in sets. And the probability, so my probability, so this probability PE2 is going to be equal to 1 multiplied by 3 over 51 equal to 3 over 51. And P1 is going to be what? It's going to be 48 over 51 divided by 2, which is 24 over 51, which equals to, because they can all be multiplied by 3, then it will be 8 over 17. Again, powerful symmetry, right? Now let's come to the third question, the drunk passenger. Okay, so do not be the drunk driver, okay, just to be the drunk passenger. A line of 100 airline passengers are waiting to board the plane. They each hold a ticket to one of the 100 seats on that flight. And for convenience, let's say that the nth passenger in line has a ticket for the seat number n. So the first passenger should be seated on seat number 1, and the 100th passenger needs to be seated on the seat number 100. And being drunk, the first person in line picks a random seat, okay, equally likely for each seat. And all the other passengers are sober and will go to their proper seats unless it is already occupied. And in that case, they will randomly choose a free seat. And in other words, if this happens, they will become what? They will become a drunk person, right? And I'm number 100. What's the probability that I end up in my seat? So still, we need to find, this seems a complex question and we don't know how to start. Again, we need to find something similar or something could be replaceable. The only thing matter with I end up in my seat is what? Is seat number 100 is occupied before me or not, right? If it has been occupied, then there is no chance I can end up in that. But as long as it is not, because all other passengers are sober, I can definitely have the chance to get on my seat, right? And how can we, but you can see this is not that even that clearly. Another thing is quite important is that seat number 1, right? Why it is the case? So let's assume the first situation where the drunk person doesn't go to number 1. Then if anyone else has occupied seat number 1 before I pick my seat, before someone picked the seat number 100, I still got 100% probability to get to my seat, right? But if the seat number 1 is always empty, then seat number 100 could be occupied because other people is going to be randomly choosing a free seat, right? And what's the probability? So now the things matters becomes event 1. Number 1 picked before number 100, and number 2 is what? Number 100 picked before number 1. And you can see these two are mutually exclusive, right? It's called happen randomly because the first person chooses his seats randomly and the second also randomly again. So what's the probability that I end up in my seat? Basically, it's 50%. Because these two is going to sum to 1 and they are mutually exclusive and they are replaceable with each other. Okay. Now let's come to our last question today. It's about endpoints on a circle. So given endpoints drawn randomly on the circumferences of a circle, what is the probability that they are all within a semicircle? You see, I think this is the most variable questions during the interview because it's super short and there's not a lot of assumptions for you to check with the interviewer, which means you have less time to think it. And it is only 1 sentence long, but it is going to take you super long time to think about that. And it is going to make you nervous. Okay. And now let's come to this question. In fact, it is a quite interesting one. So let's first draw a circle. Okay, draw a nice one. Substitute notebook. Notability, sorry. So given endpoints drawn randomly, which means each point is independent of each other, right? So since they are independent, then we can only consider the first point. We can just pick any one of them. Let's say the ith point. And all other points, each point is replaceable, right? It's the same. There's no difference between if I pick the ith point. So now let's consider the first. if I pick the ith point as the starting point, which means I'm going to draw a semicircle, which is just orthogonal passing towards this ith point. Okay, I'm going to draw that like that. And then for the second I plus 1's point, what's the chance that falls within a semicircle? It's 1/2, right? And if it's already here, then what's the chance that the I plus 2's point is also in the semicircle? Again, 1/2, right? So how many points are there left? There are in total n points, and we have picked one, so there are n minus 1 points, and each of them has 1/2's chance. So in total, we have 1/2 n minus 1, right? And this is just one situation where I picked the ith point as the starting point. Each point can be its own starting point. So in total, there are n points, and each of them can be the starting point. And for each cases, the chance is 1/2 to the power of n minus 1. And this is going to be our final solution. You see, all the questions is about to think what is replaceable and what's the same. And then using the idea of symmetry to combine them together. Because we have the total probability law, right? The total probability must be equal to 1. So the sum of all the probability I is going to be 1, no matter how it changes. This actually provides us with the equation, while it could give us a numerical solution. Okay, so it's all for today's lecture. Thank you for watching and listening. Next time we are going to talk about combinatorial analysis, which is quite important. It's about permutation and combination. I know some of you must have learned it in your high school math courses or university level math courses, but it could be super hard, right? So please, let's see some real interview questions next time. Thank you.